let us start this lecture with a thought process from Peter Atkins. Chemistry begins in the stars. The stars are the source of the chemical elements which are the building blocks of matter and the core of our subject. So, that is his belief, but of course, one can question it, that one. Let us if you recall that in the last lecture we talked about Arrhenius form of reactions and then its limitation, and keep in mind that you should not use that for a very long range of temperature. However, the temperature range is not too long, you can use it, and we have seen how we can evaluate the activation energy provided you know the specific reaction rate constant at two different temperature. Generally people use of course the several of temperature and then put a curve fitting and then do that, right. It is not that they will take 2 points and then calculate, no. First they will curve fit the data and then they will calculate what will be the activation energy, provided it is linear in nature, and if it is not little bit deviation they will make it linear. So, now let us look at elementary reactions, because in case of elementary reactions the reaction occurs at a molecular level, right. And we are taking an example, OH is reacting with hydrogen and leading to water and H, and keep in mind that H is a radical and OH also a radical. And we have seen that molecularity we had discussed earlier, but I want to again discuss this thing, and because it's important to learn what is the difference between the molecularity and the order of reaction. So, in molecularity basically number of molecules or atoms that participate in each reaction leading to a product, right. And let us consider some of the reactions which is unimolecular, and then like for example, N2O5 is decomposed in N2O4 and oxygen. In this case the reaction, the molecularity is for this reaction is only 1, that is why you call it as a unimolecularity. And bimolecular reactions, if you consider CO2 is reacting with hydrogen going to water and carbon monoxide, the two molecules are participating leading to a product. So, therefore, we are calling it as a bimolecular. Trimolecular, of course, 3 molecule will be reacting to getting into a product, right. In this case carbon monoxide reacting with O with the third body which is not participating, but however without that reaction may not occur, and that is CO2 plus M, right. And keep in mind that for elementary reaction, right, and these are not really elementary reaction, this is the elementary reactions. For elementary reaction what will be the molecularity? For example, this is like in this elementary reaction 2 molecules are reacting. So, therefore, molecularity will be 2. So, can I have a elementary reaction where molecularity will be 5 or 4, right. So, generally it is not true. Generally for elementary reaction molecularity will be always less than equal to 3, okay. Beyond that it is not possible for elementary reaction. Whereas for global reactions, which is hypothetical reactions, so that theoretical, like what we assume, there you can have right. So, whereas the order of reactions talk about the will be different than the molecularity, because that will tell you that whether the reaction rate will be dependent on the concentration and the what is its power, right, coefficients, right, power. For example, if I consider this N2O5 leading to N2O4 and half O2, in this case reaction rate what it would be? It would be the change in concentration of N2O5 divided by dt is equal to minus Kf N2O5. If I say this is your Kf, right. That means in this case order of reaction will be 1, right. Order of reaction, right, order of reaction will be 1. and molecularity is also 1. Right. So, but molecularity need not to be order of reaction for all the reaction for reactions. That might be, this is a one example where it is looks to be same, but need not to be same all the time. So, let us consider the first order reactions, as we have already seen that O2 is reacting with 2O, right, and in this case the what will be dC, if I take dC O2 by dt, if I say this is Kf is equal to minus Kf CO2, right. So, this is basically first order reactions. So, similarly you can consider S2 going to the 2H, which is then reaction rate will be dCH2 divided by dt is equal to Kf dH2, and that also you can write down equal to half dCH by dt, right. And keep in mind this is being consumed, therefore, there is a negative sign, and dH is being produced, therefore, this is a positive sign, right. And if I consider this portion only, right, what I can write down, right, I can integrate that, and separating the variable I can write down dCH2 by CH2 is equal to nothing but Kf dt, and I will integrate this thing 0 to t time here, right. Okay. So, I will get ln CH t is equal to 0 to t and Kf t at this thing. Then I can what you call get a relationship ln CS2O divided by ln CS2 Kft. Keep in mind that plus there will be a constant, right. Okay. So, in this case if you look at this will be minus ln CS2 is equal to Kft plus is equal to constant, right. Right, at t is equal to 0, at t is equal to 0, what it will be? CH2 will be nothing but CS2 comma, right, at the initial state, right. So, therefore, the constant is coming. So, if I will apply this one, then this is nothing but your CS2 at this condition, this will be CS2O. So, and this will be T, right, this will be T, T is nothing but 0, right, at T is equal to 0, this I am talking about. Then simply C is equal to ln CH2 at 0, this will be little capital, right. So, from that you can get ln CS2O divided by CS2 at time t is equal to nothing but Kft, right. Now, if you plot this thing, you will get basically slope, that is the minus Kf, right, and at time is equal to t, what is this value? This is nothing but your corresponding to ln CS2 naught at time t, right, and as it goes with the time, this is being reduced kind of things. So, you can get basically how does the hydrogen concentration is changing with respect to time, you can find it out very easily if it is a first order reaction. Keep in mind that in this case the hydrogen concentration decreases exponentially with time. Of course, this is plot in ln, but if I plot CS2, so it will very clear, it will be exponentially changing or decreasing with time. All unimolecular reactions obey the first order kinetics, right. For example, this is a unimolecular oxygen going to the O2, right, this is a unimolecular reaction. But all first order reaction need not to be unimolecular, right. There might be a two molecules will be participating, but however, there might be a situation where some reaction will be first order in nature, right. So, now and that will be occurring particularly when the one molecule concentration is too large to be changing with respect to time, then you can have. For example, if I say A is reacting with B going to C plus D, right. If I say this is Kf, I can write down dCA by dt minus is equal to Kf Ca and Cb, right. So, if Cb is too large, right, it is not really changing with respect to time, then this will be nothing but your Kf, right. Of course, this will be Ca. So, although this is basically kind of two molecules are there, and then this will be, but it will be only constant with Kf1, I can say. So, therefore, this is the and that is possible will be Cv is very greater than Ca. So, therefore, it will be unimolecular reaction. In this case, molecularity is what? Basically 2, right, but however, the order of reaction is 1. Order of reaction will be 1, first order reaction, but the molecularity in this case is 2. So, now let us look at second order reactions, right. Let us say that hydrogen is reacting with the iodine and going to hydrogen iodide, 2 hydrogen iodide, and reaction rate, if you look at, this is nothing but dCS2 dt is equal to minus Kf CS2 Ci2, and if I write down general second order reaction, we can look at A plus B going to the C and D with reaction rate specific reaction Kf, this is a forward reaction. So, concentration of species, right. So, if you look at this, this is basically reaction rate will be dCA by dt minus will be Kf Ca Cb, right. Let us assume that Cx is the things which is changing with respect to time of the concentration A and B, then Ca of concentration will be C at initial, when Ca is basically at t is equal to 0, Ca will be Ca initial, right, and similarly Cb will be Cb initial, and then that is Cb will be Cbin minus Cx. Cx is what? The concentration which is changing with respect to time, right, and that Cb is Ca is basically a Ca initial minus Cx, all the time Cx is changing, right, but Ca is initial constant, then Ca is basically changing with respect to time. And keep in mind, here we are considering for the simplicity say that both Ca and Cb is changing with the same concentration, but we need not to be true all the case, right, but in this case we are taking because to make it little simplify the thing. Reaction rate above this constant will be dCx by dt, right, is nothing but your dAi in minus Cx into Kb dCx by this thing, right, because we are saying that how it is changing, like this is nothing but if you look at this is, I can write down as x, right, changing. Now, what we will do, we will basically multiply that thing with the both the sides Cb into minus Ca1, right. So, if you look at earlier we had seen that minus dCx by dt is equal to Kf CA in minus Cx into Cb in minus Cx, right, minus dCx divided by Ca in minus Cx into Cb in minus Cx is equal to Kf dt, and then in here I will multiply it by Cb in minus Cai in, and in this side also I will multiply it as Cb in minus Cai in, right. So, both the side left and right hand side I am multiplying, that is nothing but this one. Now, this case I can write down as what I can write down here? I can write down as 1 by Ca in minus Cx minus 1 by Cb in minus Cx, right. Of course, there will be minus sign here, dCx is equal to Kf Cb in minus Ci in into dt, right. Yes or no? So, then I will integrate it. If I will integrate this thing, I will get this integrating for thing, and this is basically 0 to t I can write down, right. So, initial condition if you look at t is equal to 0, what will be Cx? Cx will be 0, isn't it, because there is no change in the concentration, right, of that. So, right, at t is equal to 0, Cx will be 0, and then if it is 0, this thing what I will be getting, this will be at t is equal to 0, this will be 0, right, and this will be 0, this will be 0, right. So, I can get basically in this case what I will get? I will get ln, right, constant is equal to ln Cbin by Cain, right, isn't it? That will get, because this constant, this is 0, this is 0, that is nothing but ln b. So, if I substitute over this in this constant, this equation, let us say this is equation 1, right, then I will get Kf as is equal to 1 over Cain minus Cbin t, right, this portion is ln this portion, right, into Cbin divided by Cain. So, this I will get a expression, right, and of course, these are all known, Cb in I all are known, and Cx if I know this concentration I can measure with respect to time, then I can find out what will be how this Kf, right. So, by this you can find out the relationship for the Kf with respect to C, and if I know this Kf, you can also find out how this Cx will be varying with respect to time, right. So, there are several second order combustion reaction which will be taking place in the elemental level. If you look at, like, these are the reaction, OH is reacting with hydrogen getting into water and H atom, and CO plus ozogen getting into CO2 and 2O, and O is reacting with hydrogen getting into OH plus H, and H is reacting with O2 getting into OH plus O, and of course, this OH is reacting with methane getting into water and CH3. Of course, some of the examples I have given here, there might be several of them which will be there in the case. So, let us now look at the third order reactions. So, let us consider the third order reaction, these are trimolecular reactions. right, 2NO is reacting with oxygen getting into 2NO2, this we had already discussed. So, if you write down this reaction, this is basically 2CNO2 dt is equal to 2Kf, right, CNO2 and CO2, right, because this is being formed, therefore, there is no negative sign. And this reaction rate, keep in mind that this is proportional to, right, third power of concentration, right, of the participating species. Therefore, this is the third order reaction, right, because this is 2 index and then this is 1. So, basically 3. So, therefore, and third order combustion reactions, some of the examples I have shown here, that is HO reacting with O getting in and also with a third body and becomes OS2 plus M, HO plus O, HO2, okay, this will be HO2 plus M, and H 3H is reacting getting into hydrogen plus H, right, 2NO reacting with O2 getting into 2NO2, right. So, these are the third order reaction what we will be considering, and in the next lecture what we will be discussing, we will be basically discussing about the reverse reaction and how to handle those things, and later on we will be looking at the chain reactions, right. So, with this we will stop over here. Thank you very much.